Hello friends, welcome to this part. In this part, I will try to solve some other problems. So this is question number 20. This question came in GATE 2016, set number 8. So we have got a buck boost DC-DC converter shown in figure below is used to convert 24-volt battery voltage into 36-volt DC voltage. So input voltage is 24 volt and output voltage is 36 volt to feed a load of 72 watt. It is operating at 20 kHz, so the switching frequency of this switch is 20 kHz with an inductor of 2 millihenry and output capacitor of 1000 microfarad. All devices are considered to be ideal. The peak voltage across the solid state switch is in voltage, so we have to find what is the peak voltage across the switch S. So let us take a quick look on buck boost DC-DC converter operation. Here is the schematic of buck boost. We have input voltage VG, let's say. We have one control switch S. Voltage across this switch S is plus Vs. A diode and output RC stage. Please note that this is a buck boost DC-DC converter, so output voltage polarity is opposite to that of input. So my output voltage polarity is like this. Now let's see what happens when switch S is on. So your equivalent circuit during on period is, so as switch is S is ideal, okay. So the voltage across S when it's on is 0. Let's see the diode voltage when switch S is on to see whether diode is forward bias or reverse biased. Now you can apply KVL in this loop. So minus VG plus VS plus VD minus V naught is equal to 0. So as switch is in on state, Vs is 0 volt. So you can get Vd is equal to Vg plus V naught. 24 plus 36, that is 60 volt. So you can see that you are getting a positive value of Vd. Now I have defined Vd in this way: positive at the anode side and negative at the cathode side. So it means that your diode will be reverse biased during when switch is S is on, and voltage across switch when it is on is 0 volt. Now let's take a look what happens when switch becomes off. So now switch S is in off state. So during on state, you have got some current in inductor and it cannot become zero instantaneously. So it will forward bias your diode and it will flow something like this. So now you can apply KVL in this loop. So by applying KVL, you can write minus Vn plus Vs minus V naught is equal to 0. So Vs is equal to V in plus V naught. So we have V in 24 volt, V naught 36 volt. So Vs is 60 volt. So the voltage across switch S is 0 when it is on and 60 volt when it is off. So the question is asking what is the maximum peak voltage across switches. So the maximum peak voltage will occur when switch S is off and it is 60 volt. So this is the answer. Hello friends. So this is question number 47 and this question came in gate 2016 set 8. So we have got a DC-DC boost converter as shown in the figure below is used to boost 360 volt to 400 volt. So input voltage is 360 volt and output is 400 volt at a power of 4 kilowatts. So output power is 4 kilowatts. All devices are ideal considering continuous inductor current, that is CCM mode, continuous conduction mode. The RMS current in the switch S is an ampere. So we have to find what is the RMS current which is flowing through switch S. So let us take a quick look on the working of boost converter. So here is the schematic of boost converter. We have input voltage source, an inductor and a active switch S. So we know that Vg is equal to 360 volt, V naught is equal to 400 volts, output power P naught 4 kilowatts. So as this converter is operating in CCM, so V naught is equal to D divided by V naught is equal to Vg 1 minus D. So where D is the duty cycle. So you can find you know V naught, you know Vg, so you can calculate D from here. So let us see. V naught is 400, 360 divided by 1 minus D. So 4 times of 40. So D is 1 by 10. And duty cycle is nothing but the on time of switch S divided by time period. Similarly, you can calculate what is the average inductor current IL. So as all the devices are ideal, so input power is equal to output power. So input power is input voltage into input current, which is equal to inductor current, average inductor current. P naught we know 4 kilowatts. So IL is equal to 360 100 divided by 9. So let us take a quick look. How does the inductor current look in CCM boost converter? So I will plot switch current and inductor current. So this is T on and this instant is time period. This is on interval when switch S is on. This is off interval when switch S is off. So when switch S is on, uh, when the voltage across the inductor is Vg, if you see plus minus VL. So VL is equal to Vg when S is on. So inductor current will build up during on interval. And you can also notice that if you take switch current IS, when switch S is on, D will be reverse bias because of the output voltage and switch current is equal to inductor current. So we can write VL is equal to VG, or LDIL by dt is equal to VG. So DIL by dt is equal to VG by L, and switch current is equal to inductor current. This is true when S is on. So as this converter is operating in CCM mode, we have some IL min, and it will start building up with a slope of Vg by L, and switch current is identical to inductor current in on period. And when switch is S is off, as it is ideal, so it will be 0. So now we have to find the RMS value of this waveforms. So there is a trick in this question. We don't know what is time interval or switching frequency of switches. It is not given in the question, but they have given one hint here. If you see, they have mentioned inductor current is continuous, and they have also given inductance value, which is 10 millihenry, and it is quite high. So the inductor ripple will be very small as compared to the average value. So we have calculated average inductor current as 100 by 9. So we can approximate this inductor waveform something like this. And when switch and if you see here, when switch S is off, so the inductor current will flow through the diode in off condition, and voltage across inductor will be Vg minus V naught, and inductor current will fall. So in off period, inductor current will fall to the same value in a steady state, and this slope will be input voltage minus output voltage divided by L. So now we can approximate this inductor waveform and switch waveform. And the average value of the inductor is 100 by 9. So this is ripple portion, and here is the average value. So we can neglect ripple portion and can make inductor current as constant to IL. So if we this is T on T. So if you neglect the inductor ripple, so inductor current will be constant, equal to the value IL 100 by 9, and switch current will also be constant during on, and when switch S is off, it will be 0. So now it is easy to calculate the RMS value of switch S. You can easily calculate it. So IS RMS equal to root T 1 by T, and this is T on. So after it is 0, so we can take a limit up to T on IS square T dt. So during 0 to T on, IS is equal to IL, which is equal to 100 by 9. So you can put this value here, 100 by 9 whole square dt, or you can write it as 100 by 9 under root T on by T, and T on by T is nothing but a duty cycle, so which we already have calculated. It is 1 by 10. So if you put, it is nothing but root D, so we know root D is 1 by 10. So if you solve it, you will get 3.5. So this is the answer for this question. So this is question number 45. This question came in GATE 2016, set 6, and this question is related to semiconductor devices. So the voltage Vs across and the current Is through a semiconductor switch during a turn-on transition are shown in figure. So this is the voltage across the switch, and this is the current through the switch during a turn-on transition. We have to find the energy dissipated during the turn on transition in millijoules. So let's say this is a semiconductor switch with voltage Vs and current Is. So we have to find what is the energy dissipated in this switch during this turn on transition. So what we can do is we can divide this turn on transition into different intervals. Let's say this is interval 1, this is interval 2, this is interval 3, and from now onwards interval 4. So the energy dissipation during first interval is nothing but Vs into Is dt. So we can see how. So let's say this is interval 1, this is Vs and Is. So Is is 0 during interval 1 and Vs is 600 volt. So you can plug this value here. Vs is 600 and Is is 0. So energy dissipation during first interval is 0 joules. Similarly, you can calculate the energy dissipation during interval 2. So during this interval, Bs is still 600 volt and Is start increasing from 0 amp to 150 amp in 1 microsecond. So this is interval 2. Vs is still 600 volt and Is start increasing up to 150 amp, and this is 1 microsecond. So energy dissipation in interval 2 is Vs into Is dt 0 to 1 microsecond. You can take this as origin. So Vs is 600 volt. Current, you can write the equation of a straight line. So slope is 150 divided by 1 microsecond into t dt. So E2 is, you can take this constant outside the integral, and if you integrate t dt, it will be. So energy dissipation during interval 2 comes out to be 45 millijoules. So similarly, you can solve for third interval. So in third interval, your Is is constant at 100 amp and Vs starts falling from 600 volt to 0 volt in 1 microsecond. So energy dissipation during interval 3 this is Vs, this is Is. So Is stays to 100 amp, it is constant during interval 300 amp, and Vs starts falling from 600 volt to 0 volt in 1 microsecond. So energy dissipation during third interval is Vs Is dt 0 to 1 microsecond. So considering this as origin, you can write the equation of Vs. So Vs will be 600 into is 100 dt. So if you solve this, it will come to 30 millijoules. So energy dissipation during third interval is 30 millijoules. So if you see fourth interval, so in fourth interval, Vs is 0 and Is is 100 amp. So if you multiply 0 by 100, 0 with 100 amp, it will come to 0. So total energy dissipation during turn on transition, total energy, so total energy loss during turn on transition is energy dissipation during first interval, during second, during third, and during fourth. So we found that energy dissipated during first interval was 0. In second interval 45 millijoules, third interval 30 millijoules, and in fourth interval 0. So total energy loss in turn on transition is 75 millijoules. So this is the answer for this question. So please like my Facebook page Triple E Helper. I will post this video on this page. If you want, you can share with your friends, and also subscribe to my YouTube channel for more videos. And if you have any doubt or query, you can either mail me or you can write in comment section of this video.